try to keep class hour. Okay? Many students are waiting there for the few guys. Okay, let me start with this page. This shows the configuration of loop gain measurement of this converter using this impedance analyzer. So last lecture we went through the details about the measurement technique and we get the result. We saw this through the video and at that time I drew this. So this is wrong. It's impossible to have this kind of phase characteristics. So in here, phase is just dipping in this special frequency range. That is not realistic. Okay, it's very hard to have this kind of thing. Okay, so the phase is decreased whole. So what I mean is phase is decreased in this manner. So all of the phase is decreased from the low frequency to high frequency. So suppose this is the new phase characteristics. Then when the phase falls to minus 180 degree, magnitude of this is 1. Okay? So this is 0 dB9. So magnitude is 1. That means what? The ratio of input and output in terms of their magnitude, they are the same. That means sustained oscillation is going on, and this converter is borderline between stable region and unstable region. So in that sense, this is called phase margin. So that means you can accept this much of phase delay, still maintaining the stability. Okay? This is the definition of phase margin, and we'll discuss in detail about the phase margin and the gain margin and the relative stability of the converter later. But this drawing was wrong. Okay, so I fixed that. Okay, and also there is many noises at low frequencies and high frequencies, and in particular the phase shows this crazy behavior here and there. So there is a reason for this, and I'll explain the reason of that noise appearance later. Okay, let me take two other examples. Okay, this is a measurement result of loop gain using several things, and there are two displays. This is one converter. This is example of flyback converter. This is example of buck converter. Here we are just showing the magnitude plot. Okay, phase plot is missing here. Okay, but there are two things. One is this is the PSIM simulation. Simulation means computational method using the time domain simulation that the frequency response can be obtained. Okay? That is PSIM simulation means computational method using PSIM software, and this black curve is the measurement result using PSM 1735 impedance analyzer. So they are about the same. Okay, but also it shows this noise characteristics at this frequency. This one at this frequency, at low frequencies, and at this high frequencies. Okay, I'll explain this origin of this noise, and this is the flyback converter example. Here we have another example. I used different converter, which is buck converter. Okay, so this data is taken buck converter, and there are four different curves overplotted in here. One is PSIM time domain model, means computational method, and the PSIM small signal model means this is the theoretical prediction of small signal model. We briefly discussed the small signal model. Using that small signal model of all the converter, this can be simulated using some simple software. So this is the theoretical prediction, and remaining tools are the experiment One is this equipment. This is HP 4194A, which is very expensive and very old equipment. Okay, this is the famous equipment. This is a legendary equipment, but this is now out of product. Okay, so digital is replacing all the analog things. So this is the analog one, so it's gone. And this is the PSM 1735. Okay. Last time I showed the video using this machine. This machine is kind of old. Okay, it's not good one. Okay, still okay. So there are differences. Okay, and the first one is there's a noise at high frequencies and noise at low frequencies and noise at low frequencies and this crazy noise at high frequencies, and noise are present not only this measurement and but also in time domain model computational method. That means noise is generated in hardware, okay, by electrical signals, and also noise is generated in time domain simulation due to the numerical garbage. There is a round of things, okay. So the garbage is appearing here, okay. That is one thing. And again, this noise is not that bad, but this area is very bad, okay. All right. And another important thing is, if you take a look at this, there's a difference in the Q, okay. This solid line is theoretical one, and this is the measurement, okay. That means there is a more damping here. The reason for this is in the theoretical model, in small signal model, we only considered the ESR of inductor and the ESR of capacitor as the parasitic resistance, but in actual hardware, there are many unaccounted parasitic resistance, wiring and layout, so on. Okay? Because of that, there is a more damping. So this peaking is reduced and phase change is less overt here in experiment. Okay? That means Q is effectively reduced. Okay? If you include all the parasitic components, maybe they match together, but this is okay. We know the origin of this. And another one is there is a dip, very sharp and big dip here. So dip. This frequency is switching frequency. Okay? As I said several times, this converter is a discrete time system in exact sense, because duty ratio is updated only once in every switching period. So there is kind of discrete time system that has this kind of characteristic. At this point is the switching frequency. Is one singular point, and this magnitude of loop gain collapse to 0. Okay? And also the integer multiples of this switching frequency will occur in this kind of dipping. So this is true. Okay? So this is captured by this one, HP1, and this PS1. I don't know. I cannot tell the difference. Okay? But this is a real one. Okay? So the computational work and the simulation of this small signal model cannot catch this. This is something else. Nonlinear discrete time behavior occurs here, and 2 of fs, 3 of fs, so on. Okay? But this is okay, because the crossover of loop gain frequency occurs well below this region. Okay? That is the fortunate. Okay? And another reason for this is, in this area, this small signal model breaks down. It's no longer valid at this high frequency. Okay? So the conventional wisdom is place loop gain crossover frequency far less than this. This is far less than this area. If you put crossover frequency here, you are seeing something false, some fake data is here. Okay? So that's one reason of limiting the loop gain crossover frequency of PWM converter well below the switching frequency. about the 20% of the frequency is the rule of thumb. Okay, we'll address that point later. Okay, and this is the additional handout I posted in LMS site. Okay, so I included this later because if you have a chance to measure this, there are some practical technique about this. Okay, so practical considerations for loop gain measurement. So this is engineering technique. This one, you are measuring this ratio between this and this with something in between. So this is pseudo loop gain. It's not a real loop gain. So TMS is pseudo loop gain, false loop gain, okay, in some sense. But this one is very similar to true loop gain. For most practical cases, no, not most practical cases. If you perform this experiment carefully, but this one, then this one will be very similar to true loop gain. This is very desirable. For that, there are some requirements. Okay. First one is this one. Impedance G2 is impedance seen into the this. Okay. This is the node Vx hat is connected, and this is the node minus Vy hat is connected. So you are seeing this impedance, which is the input impedance of this OPM compensation circuit. It has very large input impedance in general, and this is the output impedance of this converter. You are trying to minimize output impedance of this to make this converter very close to the ideal voltage source. So naturally, impedance of this, magnitude of this, is much smaller than this. That is the desirable. Okay, that minimize the difference between this pseudo loop gain and the true loop gain. So this should be the point. The select the injection point. Okay, this is the injection circuit where this condition is satisfied. One ideal location is output of this converter and input of this voltage feedback circuit here. Okay, then this impedance is much larger than this one. Then this is satisfied. Then this pseudo loop gain we are measuring will be very similar to the true loop gain. Theoretical loop gain, we discussed this, okay, using the ideal transformer. Here, this is not the ideal transformer. This port is not showed. There is some voltage delivered from here. Okay, so entirely different story. All right, that is number one. And the second one is increase the magnetized inductance. Otherwise, this transformer will be saturated at low frequencies. If you are measuring this at very low frequencies, then some low frequency sinusoidal becomes positive for a long time and negative a long time. Then transformer will be saturated theoretically. So to avoid that tragic situation, so you use tightly coupled one-to-one transformer, okay, with many windings, thousands of windings using this large core, okay, or you can use a small core with special magnetic material having the high permeability. That might be okay. Okay, the vendors are providing that small transformer. They charge sometimes 500 watts, something like that. Okay, you don't need that just to build this transformer. Okay, and keep cable length as short as possible to minimize any unwanted parasitic inductance through the cable or capacitance through the cable, between the cable, and the resistance along the cable. Okay, this is obvious. And use the high performance differential proof because the polarity, this and ground, and this and ground are different. So you need to use the differential voltage probe for the high performance. Okay. In particular, for the high voltage application, this voltage can be very large. For example, 500 DC. Then if something happens, this guy will die. Okay. So for the safety of you and your equipment, so use this probe and be very careful in proving these connections. Okay. And this one is most important. Adjust the magnitude of AC injection signal. The amplitude of this signal should be varied during the operation. In low frequency region, you use high voltage, relatively high voltage, which is this one. This is high voltage. At high frequencies, use lower than this, maybe 10 times, something like that. Okay. So next lecture slide will show the reason for this, but this is very important. This is true for the measurement and also true for the simulation. When you are using the PSIM for the computational method, you need to control the amplitude of this signal. There is option in PSIM. Okay, so you can control the initial magnitude and the final magnitude. I don't know. They are gradually changing, or I don't know, but there is just some option. With that option, you can minimize the noise. Okay, and the reason for this is to minimize noise at high frequencies and at low frequencies. All right. So maybe something else. Okay, this is enough. Okay, but you should practice to get exact or accurate measurement result. It's not easy for the first time. So you need some experience and practice. Then you will be good at measuring this. Okay, it's not that difficult if you know the principle of everything. And in this slide, I'd like to mention about something else. Okay, this is the simplified version of injection signal here. This part. Okay, this part. I ignored this and I already drew this transformer. This is not a practical, not an ideal transformer. This is a practical transformer, and the injection signal is coming in this side, Okay. As I said, the VT test voltage or injection signal is this one, because VT hat is this voltage minus this voltage, and this voltage is already minus. So minus becomes plus. So this is the relationship between this VT and Vx and Vy hat. Okay. Maybe I'll omit this sometimes because you understand there are some this head. Okay. And this is the injection signal. Okay, VT head. Again, VT is Vx plus Vy. This is the what? This is the 0 dB crossover frequency. That means gain or magnitude of a loop gain is 0, not 0, 1. That means this Vx and Vy ratio between these two is the magnitude of loop gain is the same. That means this Vt is equally shared between this and this. Magnitude of this and this should be same. Okay? This is the way understanding of this measurement, and this is divided into two equal magnitude signals, and one is appearing as Vx and the other one is appearing as Vy. So sum of these, okay, will give this. Yeah? Okay. This is the situation near this 0 dB crossover frequency. Okay. At low frequency, this operational period or frequency of this AC signal should be lower than this. Okay, that is the frequency of This is the frequency we are sweeping. So this is the middle frequency, and this is the low frequency. This is the high frequency. Okay, but this gain, this magnitude of loop gain is inherently large at low frequencies. Okay, but this signal will be shared between this, and this is much larger than this because what? This loop gain is very large. So this returning signal, Vy, is very strong. So we are seeing this strong return signal, and some of them are this one. So this should be very small. Okay. Some of them are constant. So this is very small, very weak. Okay. Then this can be ignored or buried in the noise. Okay. That is the problem. This is a weak, very weak. Weak excitation. Okay. To make this thing stronger, you need large input voltage, excitation voltage. Okay. So you are inserting this large, injecting relatively large magnitude, low frequency. Then this will be large, but this will be not that weak. Okay. Still convincible. Okay. This is discernible. Okay. High level injection means this voltage is around 1 volt this area, and discernible means some measurable or workable Vx will be obtained. This one is okay. This one is large. Okay. Under this situation, because of a loop gain is very large, this magnitude of this return signal is much larger than excitation signal. So to have discernible measurement here, this should be large. Okay. So at low frequencies, you need high level injection. Opposite is true at high frequencies. At high frequencies, this loop gain is very low. Magnitude of loop gain is very small. That means all the signal in your converter is very small. Okay. If you inject large signal, that will disturb the bias point, will cause some noise or malfunction in measurement. So to have low level injection is required not to disrupt. Disrupt to correct the measurement. Okay. So you keep the fidelity of your measurement. So this signal level, everything is small at high frequencies. So you cannot put large magnitude here. Okay. But this is also shared. Okay. So this Vx is large and the return signal is very small. Okay. That means this is very susceptible to noise. Okay. So at high frequencies, there are inherent limitations of the noise because of this operational principle and the measurement principle. Okay. Maybe the noise is coming from this measurement signal, and at low frequencies, noise is entering through this excitation signal. Okay. So always there is some noise and some crazy noise at high frequencies. Okay. And you need some skill to maintain this integrity of your measurement. All right. So you understand this, right? So typically, if I draw some real things, this is the low frequency noise, and this is the high frequency noise. Okay, something like this. And sometimes at high frequency, you will see something. This is what? This is dipole, something like that. Okay. This is some sinkhole like this. Sometimes at this high frequency. Okay. And phase is more sensitive than magnitude in noise. Okay. So you are seeing very crazy noise in the phase curve. Okay. So small change in this slope or direction of this change in the magnitude will cause huge change in the phase of that information. So typically, let's go back to this, right? So this magnitude noise is this much, but this phase noise is this much. Okay? This is a natural thing. You just ignore this and assume this is smoothly connected, and you ignore this. Okay? When writing paper, I delete this data. It's garbage. Okay? I know where it comes from, so I can delete them, right? It's not cheating. I'm using my engineering judgment. All right. And another one. This is also important. So I titled further insight on the loop gain and the difference in between true loop gain and pseudo loop gain is explained here. And this is taken from the Middlebrook's paper. His paper has this one, and everybody is using his description about this. His paper, original paper, is 20 pages long, something like that. He was very careful guy, and he elaborated everything about the practical things. Okay, but this is the key of his argument. Suppose this. So this is a converter, maybe power stage and the feedback compensation, and this is maybe modulator gain, something like that. I don't know. Okay, somehow we divide in the middle, and we inject Vx, and it will go around here and come back here. That will be the Vx, returned Vx. Okay, so this situation is very similar. Similar to the case we used ideal transformer to explain the concept of the loop gain when we start talking about this loop gain measurement. Okay, you remember that, okay? Later on, we replace the ideal transformer with the practical transformer. Okay? So this is a true loop gain. This is real loop gain, and this is the functional block, and this is modeled as voltage source. And one assumption here is there is an input impedance is very large. This is assumption. And this part, block 2, is also modeled as voltage source. And assumption here is output impedance of this thing is very small, can be ignored. This might be true for the OPM-based compensation. This is very large. And this might be true for something, maybe our PWM converter. Input impedance of a PWM converter is very large, closed one. Then this assumption is valid. Okay. So this you start here. Vx appeared here, and this is a dependent source. Output of this is Vx times some gain, G2. Okay. Open voltage gain, open circuit voltage gain. This is output is sensed through this PWM block. And this, consider this as the PWM gain, and go back and something like that. Okay. When you are considering the loop gain, the input signal is grounded. Okay. Input is 0, only considering this feedback test. Then first you start with this G2 Vx. Then start with the Vx and multiply G2 and multiply HS. This is error signal. And multiply G1, so G2 HG1 is the voltage across this port, and that is then this will be the voltage division between G1S and the G2S. So this is the equation, right? This is the equation, and you have minus sign here, and considering this loop gain, we put additional minus sign because we make this one positive, okay? So we intentionally put minus here, so this becomes positive. So this is the equation for the true loop gain, okay? This is one equation, but if you put this equation in this way, this is the much more useful. So you take out this, and you send this thing to this side, okay? It's the same equation. Right? So this is this, okay? So this is the expression for the true loop gain, and somehow the Middlebrook, he rearranged in this manner, but this is very important. This will provide some critical connection between this true loop gain and pseudo loop gain. That will be discussed in the next slide, okay? Next slide. So now we consider this real situation, practical situation. So this is what? This is practical transformer, and this signal is appearing across this. So it has some sinusoidal source, and GSS is the source impedance of insertion circuit. Okay, so this is maybe Thevenin differentiation of that circuit. So it's located here, and this voltage Vx, it goes around here and come back to here, and this is Vy. Okay, this is the way we are measuring the loop gain with this transformer isolated AC insertion. Injection, okay, insertion, injection, AC injection. Okay, this is the true case. All right. Then what we are measuring is ratio between this and this. It's not true loop gain. Okay. True loop gain is this one. You start from this Vx and measure the returned Vx. Okay. That is possible when you use ideal transformer. When you, okay, so you understand this, right? We went through this, and this is the practical case. And because there is something in between for the AC signal injection, so they are separated. We are measuring ratio between this and this. Okay, we are considering that as a loop gain. So that loop gain is the pseudo loop gain. Pseudo loop gain is T prime S is ratio between Vx and Vy. We don't need any minus sign here because this is already polarity is inverted. So same as the having additional minus sign. Instead of that, we swap the polarity of this. Okay, then start from here. So Vex is this one times this, and times this is this error signal Vx. Okay, and minus Vy is this signal is this one, and there is a voltage drop between because of this, and we define Is here. This is very critical. So Is is defined here. So this is true. Okay, this is a very simple circuit equations, and Is is given by this Vx divided by G2S is Is. Okay, and you combine these things together, or you put this one here. So from these two equations, you eliminate this. Okay, then you have this. Okay, you have this. Vy measured here is related with Vx through this equation. There is no loop gain equation here, but you divide this Vx to here, then this term is what? This term is pseudo loop gain. You want to measure T prime S. Okay, so T prime S is this one. T prime S is this one. We know this, right? In the previous lecture slide, we found out this 3 multiplication term is this one. Okay, then you replace this here. Instead of this, you use this. Then there is a relationship between this pseudo loop gain and the true loop gain. Okay, this is almost magic, right? So this is the equation, final equation. It indicates the relationship between true loop gain and the pseudo loop gain. There is some impedances. Okay, if you see something like this, what you will do? You use the asymptotic analysis technique. Okay, maybe you learn from the last course, last semester lecture. Okay, exact expression is very complicated. Okay, you cannot do anything from this, but if you use asymptotic analysis, okay, this is called asymptotic analysis. This is the equation number 5 in the previous page is this one, and you divide this one into 2 separate approximation or expression, and when ratio of this one is much larger than this, then this will be gone, and you are comparing this and this ratio is much larger than this, then T prime S is the same as this one. Okay, so this is the simplest case. Okay, when this ratio is much larger than I'm sorry. This ratio is much smaller than 1 because G2S is much larger than G1S usually. Okay? We select that point as the signal injection point. So this is very small. Okay? Then this is ignored. This is ignored. We are comparing this and this. This is small. Then it is also ignored. Then you get this. Okay? And this is the very small compared one. Then you ignore this. Okay? But loop gain can be very small at high frequencies. Okay? So then loop gain is not much smaller than, much larger than this for some case. Okay? So for this case, this condition is easily satisfied, but this condition can be violated. For that case, you use this. Okay? The pseudo loop gain, relationship between pseudo loop gain and the true loop gain is, if you measure the pseudo loop gain, then you add this term to there. Okay? That becomes true loop gain. Okay? So, or vice versa. Okay? Somehow you know the equation of the true loop gain, and when you are measuring this situation, what you are getting is some frequency range, you will get the true loop gain, and some frequencies you will get this. At that frequency, this magnitude of this one is much smaller than this one, then loop gain simply becomes this one. Okay? So there is a chance of false measurement at high frequency always, but it may occur at very high frequencies when ratio between G1 and G2 is very small. If this one is very small, this one is very large, then that won't happen. Okay? So this is the method. Okay? And we are inserting this voltage source. This is called the voltage source insertion. There is another way of measuring this loop gain. Maybe you insert current source, current disturbance in parallel with this. This is, for some case, that has some advantage, that approach has some advantage. Okay? When first publishing this paper, Dr. Middlebrook proposed all the possible way of doing this. Okay? So this is very brilliant job, and this can be applied all the PWM converters and all the feedback audio amplifiers and all the feedback systems. Okay. Before him, there is no one knows how to measure the loop gain in operational condition. Okay, now everybody knows this. This is commercialized. Okay. And this can be used. Okay. The big question is, what happens if you have initially unstable converter? Still, this method can be used. Okay, with some modification, and with that modification, you can still measure the unstable loop gain of your converter. Okay, I'll go details about this asymptotic analysis and measuring the unstable converter, loop gain converter, because that is the one problem of your midterm test. Okay. So maybe I hope you think about that problem or dig out some useful reference book. Okay, then refer to them, and you will learn this by yourself. Okay, how to measure the unstable system. Okay. All right. Before leaving this page, I'd like to summarize the content of this lecture slide. This equation number 5 came from the previous lecture slide, and this equation describes the relationship between true loop gain and pseudo loop gain you are measuring using this AC injection technique. And you have this term, okay? And usually this injection point is selected where the impedance seen this direction, G2S, is much larger than impedance seen through this direction, which is G1S. So if that is true, this term can be ignored. Compared to this one, then equation becomes TS plus G1S divided by G2S, which is this expression. And if further this condition is satisfied, which says the magnitude of G2S, this one is much, much larger than ratio between G1 and G2. If this condition is satisfied, we ignore this, then remaining term is only TS. For that case, this pseudo loop gain is virtually same as this true loop gain. So this is the desired case. Okay. So this is the first one. But if this condition is satisfied, so we ignore this, then we have this expression. But magnitude of this one is much larger than this one. Then we still need to keep this. For that case, which is this case, so this is the first condition, and this second condition is not met, it does not satisfied, then we should use this as the approximation of our pseudo loop gain. So for this case, pseudo loop gain is very close to the true loop gain, but in this case, pseudo loop gain is same as true loop gain plus some additional term. Hopefully this term will be very small, so we have good approximation for both cases. Okay, there is our desired goal here. And one very critical comment on this is the presence or magnitude of this GSS, which is the source impedance of AC injection source. Okay, so this is the source impedance, some impedance coming from the AC injection source. For our example, that is the sinusoidal voltage source combined with practical transformer, and this source impedance is totally independent of this evaluation of this pseudo loop gain. Okay, so this expression 6 is valid regardless of the presence or value of GS. So you don't have to worry about presence of this, and you don't have to worry about this. That is very, very important. Okay. All right. So I think this is the end of first session of this lecture, and we'll take a short break. And after this break, after a short break, we'll discuss some details about this with two separate lecture slides. Okay.